we're ignoring the solute in yellow and not the solute in purple. Okay, so I may have flip-flopped the colors here. So if we're completely ignoring the solutes in yellow, which are urea, we're only taking into account the solutes that cannot cross the membrane, then we're only looking at the purple solutes. And so the inside has a higher solute concentration. The outside has nothing, essentially, if we're ignoring urea. And so this creates a hypotonic solution in the extracellular fluid. All right. Let me pause here and see what questions come up, and then we'll keep going with this final example.
I'm sorry, I kind of missed it. Can you explain what the gradient is for osmotic pressure one more time?
Sure, yeah. So the osmotic pressure, we said, was created because of the pull exerted on water. Now, water is being pulled to the side that has a higher solute concentration, but has a lower water concentration. And it's being pulled from the side that has a higher water concentration and a lower solute concentration. So we can see here that water is moving down its own gradient, but it's moving against the solute gradient. And so the force that's created here, that's actually pulling water from one side to the other, that's what we refer to as the osmotic pressure, okay? And you can also think of the osmotic pressure as the force that would be required to stop this flow of water. How much force would I have to exert to interrupt this flow of water? We can also think about the osmotic pressure as that value as well. So what kind of force is required to pull this water from one side to the other? Or what kind of force would I have to exert to interrupt or to stop that water flow from side one to side two? Okay. Let's see what other questions come up. Okay, excellent. So someone is asking me to repeat the difference between tonicity and osmolarity once again. And I kind of had a flip-flop with those, so I'm going to definitely repeat that one more time in the interest of just correcting that and making sure we have that straight. Okay, so when we talk about osmolarity, we're talking about all the solutes dissolved in either solution. So we're going to take into account solutes that can cross the membrane, as well as solutes that cannot cross the membrane. So in this first example, this is an isoosmotic solution because we've got 300 milliosmol inside the cell. We've also got 300 milliosmol outside the cell. Now, it so happens that these are different solutes dissolved in both of these solutions. When we look at the tonicity of the solution, it's different because we're going to completely ignore the solutes that can cross the membrane. So I was saying before, we're ignoring the solutes that can't, and that's incorrect. We're ignoring the solutes that can cross the membrane. So urea can move freely across this membrane. The membrane is freely permeable to urea. So we're essentially going to ignore urea as we speak about tonicity of the solution. So all we're looking at are the impermeate solute, or the solute in purple, which cannot cross the membrane. And so looking at that, we've got a higher concentration inside the cell. Okay, it's greater than 300 milliosmol. But again, we're ignoring the fact that urea is present outside the membrane because urea can cross the membrane in question here. And so essentially we have solutes inside and no solutes outside. So we have a hypotonic solution here, although we can think of it as being an isoosmotic solution as well. And this is the essential difference between osmolarity and tonicity. Osmolarity considers all the solutes dissolved. Tonicity only considers the impermeate solutes, or the solutes that cannot cross the membrane in question. Okay, I really hope that clarified it because I really kind of flip-flop these at the beginning. Any other questions come up about this? Okay. All right, so let's keep moving along here. This is again a nice table to kind of help explain the difference here a little bit. Here it says osmolarity, total concentration of permeate and impermeate solutes, tonicity being only the concentration of the impermeate solutes. Again, only the concentration of the solutes that cannot cross the membrane. We completely ignore the concentration of anything that can go through that membrane. Let's see, another question here. So someone is asking what an isotonic solution would look like. Excellent. So an isotonic solution, let's go back to this image here. Here, an isotonic solution would look like having that impermeate solute both inside the cell as well as in the solution outside the cell, okay? Or if we had the exact same scenario, but the membrane was impermeable to urea as well. Okay, I'll say that again. If we were to have an isotonic situation or an isotonic solution, that would be if we had the exact same impermeate solute in the cell as well as outside the cell, or if we had the exact same solute concentrations as we do here, but the membrane was impermeable to urea as well. Okay, so we would not see the movement of urea into the cell or out the cell. Okay, excellent questions, excellent questions. Any other questions on distinguishing these two? Okay, great. In this final example here, we'll just kind of apply some of that understanding, some of that information. So basically we've got two cells suspended in two different solutions. So in part A, we've got a greater solute concentration inside the cell, 300 milliosmol. We've got a lower solute concentration outside the cell. And so over time, what we see will happen in order to equalize the osmolarity is that movement of water is going to take place. Now, can anyone predict here in what direction we would have movement of water for part A? So where will the water move in order to get us to this situation here? What's the direction of water movement?
From the inside of the cell to the outside.
So someone says from the inside of the cell to the outside of the cell. That's not correct, but I've got some other people here saying into the cell. Okay, so the water will move from the outside of the cell into the cell. And I really want to make sure that we understand why. Okay, so a lot of responses saying going into the cell. So that is absolutely correct. So because we have a higher solute concentration inside, meaning a lower water concentration, we've got a lower solute concentration outside, meaning a higher water concentration. We can think of this as either side. We can think of this from either perspective. Water is going to move according to the water gradient, so from high to low, but you can also think of it moving against the solute concentration, so from a low solute concentration to a high solute concentration. So that's going to allow the water to move from the outside of the cell to the inside of the cell. And we can see that being exhibited here as the cell begins to swell, okay? So water moves according to its gradient, high to low, or against the solute gradient, low to high. Okay, let's look at the scenario here in B. So we've got a high solute concentration outside the cell, a low solute concentration inside the cell. And so what kind of movement, what direction of water movement do we see in order to get us to the scenario where we have an isoosmotic solution or isoosmotic state here? Excellent. So water is going to move from the inside of the cell to the outside of the cell. Perfect. And so that's exactly what we see here as we see the cell beginning to shrivel up as water moves from the inside of the cell to the outside of the cell. Again, taking into account here that water is moving from a high water concentration inside to outside and from a low solute concentration, again, inside to outside.